Hello, my name is Evan Suma Rosenberg from the University of Minnesota. I will be presenting our paper, Capture to Rendering Pipeline for Generating Dynamically Relightable Virtual Objects with Handheld RGB-D Cameras. This work was completed by my PhD student, Qifan Chen, at the University of Southern California. As he has since graduated and recently welcomed a new baby into the family, I will be presenting it on his behalf. Many of the people in this audience probably have firsthand experience creating virtual reality content, so I probably don't need to spend too much time explaining that this process can be time-consuming and expensive. Our goal in this work is to enable automatic creation of VR content by capturing real-world objects with widely available low-cost hardware. Any such system would need to be portable, so it can easily be brought to capture an object in situ, and also usable by non-experts, meaning people who do not have PhD-level knowledge of computer vision and 3D reconstruction. These requirements introduce some notable technical challenges due to the fact that the camera movements are typically unconstrained, and often this means that they have both the spatial and temporal coverage of the object is inconsistent and unpredictable. Existing approaches can be roughly divided into two categories. First, there are purely image-based techniques, also known as light field rendering, which are impractical for multiple reasons and also don't typically allow dynamic interaction. Second, purely model-based techniques are fairly ubiquitous nowadays. While these methods support dynamic interaction, the textures generated are typically static, and the visual quality is typically reduced due to blending multiple images. This is particularly problematic when specular highlights are present, which makes the object appear blurry. These artifacts are even more noticeable in virtual reality compared to desktop viewing due to the lack of view-dependent appearance changes that would naturally occur with head tracking. A hybrid technique known as view-dependent texture mapping can solve many of these issues. As you can see on the left, the visual detail is improved compared to a purely model-based approach. However, VDTM suffers from artifacts and discontinuities in transitions between viewpoints when the camera movement is unconstrained due to the incomplete coverage and missing data. The method shown in this video also operates at only 15 frames per second, which is unsuitable for virtual reality. In this work, we developed a complete end-to-end capture to rendering pipeline, which starts with an RGB-D image sequence captured using a handheld device, such as a Microsoft Kinect or RealSense camera. The depth images are used to generate a geometric model, and the color sequence is then subjected to a keyframe selection process that results in a subset of the best frames for texture reconstruction. We developed a novel method for separating the diffuse and specular maps from the color images. The specular components are then combined with the geometric model to estimate the illumination in the capture sequence and the surface material properties of the object. All of this data is then brought together in a shader-based rendering model that can produce photorealistic view-dependent renderings of the object, suitable for real-time viewing in virtual reality at rates up to 90 Hz or even more. Note that this research is primarily concerned with plausibly realistic virtual reality experiences that work in real time. Computing physically accurate surface reflection models is not strictly necessary, and as such is beyond the scope of this work. Let's take a slightly deeper dive into the capture and reconstruction stages of the pipeline. Due to time constraints, I'm going to leave out most of the equations and low-level technical details, which can be found in the paper. Our approach would be potentially applicable to images captured using any RGB-D camera. All of the results shown in this paper were generated using sequences from a large public dataset of object scans, which were captured by non-expert operators using a handheld PrimeSense camera. Remember PrimeSense cameras? The geometric model was generated using a straightforward application of the widely used Kinect fusion algorithm. This process also computes coarse camera trajectories. Given how ubiquitous this method is, I'm not going to describe it further here. Kinect fusion typically uses temporal sampling to identify a subset of color images for texture processing. In this work, we use a superior method. First, we sort color frames by their blurriness, and then we begin selecting only those greater than a minimal distance threshold away from already selected frames. This provides a balance between better image quality and spatial coverage. Because the camera trajectories from Kinect Fusion have coarse accuracy and are also subject to drift over time, we then apply an iterative color mapping optimization algorithm from previous work to refine the alignment of each camera frame. This optimization is also applied at later stages in the pipeline to further improve the results. Next, we then need to estimate the illumination and surface material properties. Our approach leverages the fact that specular highlights are view dependent, meaning that they will vary across the image sequence. The diffuse components, however, should remain constant across the image sequence regardless of the camera's viewpoint. In a normal rendering pipeline, the diffuse and specular components can be combined to produce a realistic rendering of the object. Low-rank decomposition essentially does the opposite and extracts the separate diffuse and specular maps from the combined color image. Okay, if you really want me to prove this is a hard problem, here are some equations, but please see the paper for an actual explanation of how this works. In this work, we are using the well-known Phong shading model. After the maps are separated, we use the specular maps and the surface normals to estimate the number and direction of lights in the capture scene. The specular highlights essentially vote for lights, and a mean shift clustering is used to find local maxima. We then apply an optimization that computes variables for the Phong shading model, namely the color of each light, the specular constant K, and shininess coefficient, which are necessary for the model to be able to produce specular highlights on the rendered surface. Base textures can then be generated by blending the diffuse maps, after another round of color mapping optimization using only the diffuse components. The specular components actually were contributing to error back in the combined images. This image compares the computed diffuse texture with and without low-rank decomposition. In the middle column, you can see that the specular highlights were blurred into the texture. On the right, after the separation, they were mostly removed, although it should be noted that some artifacts do still remain. Okay, now let's show the final results. Because these effects are view dependent, they are not really evident from static images, and really, video doesn't even do it justice either. The best way to experience this is with a live demo. All right, so what you'll see now is that we have one of the sculptures that was in the scanned object database in front of me, but there's no view dependent effects. That's because this is currently being rendered with the default method of static textures generated by Kinect Fusion. You can see now I'm going to turn it on, and we can compare against the reference video up there. And you can see I'm getting immediately a lot of specular effects, but also the diffuse texture. You can see the diffuse texture quality is also better because the highlights aren't being blurred into it. And you can see as I move my head back and forth, I get the nice motion parallax. I'm just going to quickly show the two other objects that we have. You can see here, this is the antique chair. Again, we get a lot of nice specular highlights and good detail. We do see that there's some like chromatic aberration there in some of those ridges, but that's likely due to the fact that this is really a low resolution center. Remember, this is only VGA, and so we get better quality results with higher resolution sensors like a RealSense. Note the green arrows. The green arrows here are actually the lights that are computed from the original scene. So this is actually the directions and of the lights that we are placing in the virtual scene to match the real scene. Okay, so that hopefully gives you a good idea of the fact that these recreations are plausible. I'm just going to quickly show you the dynamic relighting. I'm going to do this by creating some spotlights and turn those up and move them around. So you can see we're actually not just limited to recreating the illumination from the original scene, which is typically what view-dependent texture mapping does because it uses the original images and blends them together. However, we're actually able to recreate arbitrary lighting using and even changing the color of the lights is possible. Because we know the surface material properties, and we're not actually using those original color images to generate the specular highlights. So I'll just reset the color here right back to normal, and then we'll wrap up. Okay, so hopefully that demonstrates the dynamic relighting capability. I could actually stay in this demo for a long time because it's really fun, but let's go ahead and wrap up. To summarize our contributions, we presented a novel texture synthesis approach that jointly solves for diffuse and specular decompositions and optimized camera poses. We then showed how to estimate the scene illumination and material properties using the extracted specular maps. We presented a real-time rendering model that can plausibly replicate object appearances at frame rate suitable for virtual reality. That means 90 Hz or greater. And finally, all of this was encapsulated within a fully automatic capture-to-rendering pipeline that can serve as a reference for implementers of these systems. Our approach makes several assumptions about the capture conditions that could be addressed in future work. There are also numerous opportunities for extensions and improvements, such as supporting a wider variety of lights, smarter vertex optimization, and integration of alternative methods for texture separation that have been discussed in the literature. We are also particularly excited about the potential of using this approach in augmented reality to create dynamically relightable objects that can adapt to the user's real-world illumination. Assuming you are watching this live and not a recording, I am happy to take questions. However, please note that any low-level technical details are probably best directed towards Chifan via email. Thank you all for listening.